Now let's revisit the derivatives of integrals. Let's suppose we have an integral like so. We've got t up there, and maybe we'll put our usual a down there, and we've got some function, let's keep it general, little f of x dx, and I want to find the derivative of this thing with respect to t. So in chapter 8 we started taking the derivatives of things other than the x. You know, we're doing our static analysis. Now you want to pay attention, right? So we've got a t here, we've got a t here, but remember that's an x. So how are we going to take the derivative of this thing? Well, it turns out that it's really quite simple. If you remember before, the derivative of the integral gave us, they just sort of canceled each other out. And here something very similar is going to happen. This is going to be equal to just f of t. We're just going to evaluate this little f t, the integrand at t. Or I could have written it in a little more complicated fashion. I could have said, well, we're going to integrate and take the derivative, but that would just be f prime of t, big F prime of t, which is just our definition of little f of t. And so you can imagine, imagine d of dt with a t up there and a constant down at the bottom as stretching the graph. Right, we've kind of got a function, and maybe it looks like this, and t is right there, maybe a is there, and we're going to move t over to the right. I didn't give myself a lot of room, so I'll have to make the curve just a little bit bigger. Imagine what would happen if we move t over there. Well, it's going to get a little bit bigger. In this case, with this function, it should get a little bit bigger. And so kind of imagine that this distance down here is being stretched out to the right, and the lower bound is fixed. A is not changing, t is getting larger, and so you're integrating over a larger area, stretching the graph. You're integrating over a larger area. That's the way I think of it. You could imagine the opposite. If you made the change in t negative, you could be making it shorter, but what you're doing is you're kind of changing how big that x-axis distance is. And so it makes sense if you've got a function like the one I've drawn, if t is getting larger, then the area is going to get bigger. And if that t upper bound is getting smaller, then you think you would, and the distance is getting shorter, you'd expect the area to get smaller. And well, I'm going to erase everything. Now maybe I didn't erase everything. Let's take a look at an example. So suppose I have suppose I just have t up there, and I've got 0 down here, and I want to find the derivative with respect to t of the function x squared minus log x. Put it in brackets, dx. What's that equal to? Well, it's just going to be equal to t squared minus the log of t. So I plug the t into this integrand. I don't even have to integrate. The derivative and the integral will cancel each other out. And so here's my answer. Now let's talk about the lower limit of integration. And so I'm going to draw a definite integral. I'm going to put b as the upper limit, and I'm going to put t as the lower limit this time. And I want to take the derivative of this thing with respect to t again. So I'm going to take the derivative with respect to the lower limit. Now I'll write it formally. So we've got f of x dx. What are we doing here? Well, now imagine that we're making the lower limit smaller. So if I draw a diagram, and then here's my function f of x, and I've got t here. Oh, excuse me, I've got b here, and I've got t here, and I'm keeping b fixed, and I move t to here. Right. Then we're sort of squeezing or shrinking the distance. And what does that look like going back up to here? What's this going to look like? I'm going to evaluate the function at the negative. So if t is getting larger and b is held constant, we're going to shrink the distance. The distance is going to get shorter. We're going to shrink the area that we're evaluating. And so I'm going to get negative f evaluated at t. Or I could write it like, after integrating, we take the derivative and then evaluate the function at t. Oh, and I should make sure I don't forget my negative sign there. All right, so if t is getting larger, in this case, we're shrinking. We're shrinking the area. Now you're probably wondering, but Professor, what happens if the upper limit and lower limit are functions? Well, I'm glad you asked, because that's the next case that we're going to look at. What happens if the upper limit and lower limit are functions of t? Now notice that we're talking about t here. We're not talking about the variable of interest, the x. We're talking about the limits, the upper limit and the lower limit of this definite integral. And what's going to happen here? Well, we can see here if we, changing t, changing t is going to change both the upper and lower lower limit. So I'm going to combine the two rules we just learned, and I'm going to write, well, I'll write it up here. This thing is going to be equal to f evaluated at the upper limit. But because we're taking the derivative, I also want to apply the chain rule. I'm going to move this down here out of the way. And so that's the first part, right? I'm evaluating, take the upper limit, I plug it into the function, but there's also, we have to keep in mind that this function is going to change. So we need to know by how much the upper limit is changing. And to do that, we apply the chain rule. So we have that nice little term there. And I'm going to minus, and now I'm going to apply the rule to the bottom. And similarly, I'm going to evaluate our integrand at a of t, but I also want to apply the chain rule and note how a change in t affects our lower limit. Let's do an example. We've got an upper limit of t and a lower limit of negative t. So we're trying to find the area between t and negative t. And we also want to know how this area is going to change if we were to change t. So I'm going to write this out as I want to evaluate this function at its upper limit. So I've got 1 over t to the power of 4 plus 1. the derivative of t with respect to t is just equal to 1. Or maybe I shouldn't have the t up there. Just the derivative of the upper limit with respect to t is equal to 1. So I could just put a 1 there. If I forgot about it, it wouldn't make a difference. Now I want to subtract off the lower limit, or the integrand evaluated at the lower limit. So I'm going to have 1 over the square root of t negative, oops, didn't give myself quite enough room there, minus t to the power of 4 plus 1, and then all that in a square root. I also need to find the derivative of the lower limit with respect to t, and that's going to give me negative 1. And this whole thing times negative 1. Now, oh, and keep in mind I found that I forgot this little square root right there. Now all I have to do is simplify. And so I've got 1 over the square root of t4 plus 1 minus a minus becomes a plus, 1 over. Remember that was negative t to the power of 4. That's just t to the 4 plus 1, and the whole thing to a square root. And so I get 2 divided by the square root of t to the power of 4 plus 1. All right, you try one. Press pause on the video, give it a try, and when you're ready, press play, and we'll work through it together. Now you can see that we're being asked to find how this integral is going to change if we change the lower limit t. So to answer this question, I want to take the negative of the function, this thing right here, and I'm going to evaluate it at t. So I'm going to get negative e to the negative t squared. And that's it.